Hello class, this is Ms. Io with today's video on sections 12.3 and 4, application of vectors in the dot product. As you're watching the video, please write down important vocabulary, formulas, equations, and examples in your notes. Feel free to pause or rewind the video as often as you need to get a clear understanding of what's occurring. And at the conclusion of watching the video, please write a brief summary as well as place a top question in the online list the day before class. All right, let's begin. I talked about this briefly in class the other day, but I want to talk about it here. Vectors, we like vectors because the position of the beginning and end point changes, but the vector qualities stay the same, which is the horizontal component, in this case is 3, I, and the vertical component is 4i. And these are the different ways to represent this vector. This is in component form. This is in vector form, which tells you instead of using I and J, they just understand that the first term represents I, the second term represents J, direction. And then this term also represents a vector without the arrow. The vector is bolded, and we have brackets to represent the components, the horizontal first and the vertical second. Okay, all right, we're going to look and see where vectors are used in situations outside of math today. Really, vectors are used in situations where you have multiple quantities and you have multiple information about multiple quantities. And so a vector in n directions basically represents n quantities. Let's take a look at an example. In this case, this is in the concept of population. And in population, we have the population for 6 New England states. And here are the 6 states. And the values of the population will be going into the place of these vectors. In this case, this is a value for the 6 states in 1995. And this is a value for the population in the states in 2005. Okay, so they asked us to do several things, one of which is to find out what the difference is between the population in 2005 and population in 1995. Okay, so that's what this quantity is going to represent, the distance. And to figure that information out, all we do is we subtract the two vectors. Now, graphically, you might have had challenges with subtraction, but numerically, it's very simple. We basically pair up the first coordinate with the first coordinate and subtract it, the second coordinate with the second coordinate and subtract it, and vice versa. So in the end, we get an end result, which is equal to this vector. And this vector basically tells you the difference in population years, and the difference in population between the years 2005 and 1995 for each state. So in other words, here we have 0.23 million for the first state, which was Connecticut, 0.08 million for the second state, which is Maine, and vice versa. Now they said let S be the estimated population of New England in the year 2015. So we have some other vector. How do we estimate that? Well, they said in this case we can estimate it by essentially adding the population of 2005 plus twice the population of plus twice the difference of the population from 1995 and 2015, and that's S is equal to Q plus 2R. So they give us a formula, so life is easy. They want us to find S, and you can find S by doing that calculation as well, Q plus 2R. So we take, for each term of each of the vectors, we add Q plus 2 times the R vector, and we get this information. You can take a look and see. And then a second situation saying that we consider that T is equal to 1.08 Q, and this is the population, another estimation for the population in 2015. So we don't actually know it because, well, at that time, they didn't know what the population is. So to figure out this, we do the exact same thing. We use our properties of vectors, and we end up, it's right here. Sorry, we end up with, oops, this is our answer. by multiplying each component of the vector by 1.08. Okay, very simple math here, but it's an example of vectors not in math but in other areas. Let's take a very quick look at economics. After Harry Potter, this is the next most financially successful movies in order: Shrek, Pearl Harbor, and The Money Returns. And if S, T, and U are the revenue vectors, which is how much money each of those movies brought in, then you have something that looks like this. If you notice, this tells you it has just one component, which is the amount that the respective movie brought in. So if they want to find the total revenue of all three of these movies, you just add up those values. And as you can see here, there you go. The next example is about P, which represents a price vector at a car dealership. So you have N different types of cars, and each component represents the price of each respective car. And C represents the consumption vector, which is for each respective car, how many models are sold during that month, during a particular month. So if I want to take a look at, let's say I gives the number of cars each model has directly in inventory. Okay, so what will I minus C represent? Well, this is the amount in inventory for each respective car minus the number of cars that are sold in a month for each respective car. So I minus C basically represents how many cars are left over in inventory after 1 month. So, and it will give you the value for each respective type of car. I minus 2C, well, 2C indicates 2 months of consumption. So how many cars are left after 2 months of consumption in the inventory? And then over here we have C is equal to 0.3I, which represents a third, or 0.3, or 30% of the inventory represents how many cars are sold in a month. So we have different ways to represent that, all using vectors. Not difficult. So now let's take a look at it in physics. Another situation. If I want to find the force that Earth applies on Earth, and I'm not a physics person, or the force that the moon applies, then we can use this physics formula. Constants are G, M, and E. G and M, which are the same, and the mass of the moon, mass of the Earth, and divided by R squared over E, which represents the distance from the Earth, distance from the moon. Really, that's the magnitude of a vector squared. And to figure out this, we find the magnitude of R sub E. And we can find that by taking this component squared plus this component squared and taking the square root, but then we would square it back all over again, and vice versa. In this case, for R sub L, I think this is R, and then we have our answer. Just want to show you examples. Okay, and here's another example using computer graphics with position vectors. This is my start point, and this is another start point. If I move them the same exact way, the question is, where will the resulting point be? Well, oops. So I take this, I can easily do this and figure this out. The resulting point here would be over here, and resulting point for here will be over here approximately. Well, how do I find that value without a graph? Well, you find it using first breaking up this vector into components. As you can see here, this is the component form of this same vector. Okay, and then we're going to basically add the components to figure out the end result for P. We take the start point and we add the displacement vector. And since we've broken up into components, we can add the I components to each other to get this I, the J components to each other to get this J, which is approximately around this point right here. We do the exact same process for the other one. We look at Q start, and add it to the displacement vector D, and add I components together to get the new I component, add J components together to get the new J component, and as you look here, it seems to be close to it. Well, yeah, 8. 4.819. Okay, very close. So that's how you would use vectors. Okay, moving on. Dot product. Now, some of you ask, how do we multiply vectors? Well, it's a little bit different. We don't call it the multiplication of vector. We just call it the dot product. And to basically compute the dot product, we basically multiply each coordinate of u by the corresponding coordinate of v. And then after we get each of those products, then we add the products. That is called the dot product. And we write it as this vector with a little circle or dot in the middle times v, to v, which represents the multiplying of the dot products. And the end result is the dot product will be a value, which is a scalar and not a vector. So in the past, when we added and subtracted vectors, we ended up with another vector. When you multiply, i.e. dot product vectors, you end up with a value, not another vector. And here's the process in algebraic form. Again, multiplying the components of each corresponding vector and then adding the results. So let's take a look at an example. If this represents my consumption vector, how many cars I sold in a month of this respective type, type 1, type 2, type 3, type 4, type 5, and the P vector represents in thousands the price of each respective car, type 1, type 2, type 3, type 4, type 5. To figure out the total revenue that the car dealership made off these 5 cars, we multiply the amount of type 1 times the price for each type 1. We multiply them the number of type 2 times the cost of type 2 cars and vice versa. And we end up with this statement, which is the result of adding each type. So this times this gives me this, and vice versa. This times this gives me this. And you can do the same, and then you add all the results. Not difficult. Certain properties of the dot product. You can also calculate the dot product if you know the angle between the two vectors by multiplying the magnitude of each vector times the cosine of the angle. And there's a proof of it in the book, and we'll look at an example or how to use that in the GEA. Order doesn't matter for the dot product, even though order doesn't matter in any type multiplication. So u dot v is the same as v dot u. And then we can also distribute it as well. And then if I have the same vector being the dot product of itself, I can figure that out by taking the magnitude of the vector squared, and that's related to this because the cosine of the angle, well, the angle between the two vectors is going to be 180, so the cosine of 180 is, well, 1 or 0, depends how you look at it. So u times v times cosine of 180 or 0, which is 1, then that implies, I'm sorry, did I say 180? That doesn't make sense. 0. Okay. Cosine of it's the same vector, the angle between the two is 0. So the cosine of 0 is 1. So this basically represents the same. Just to show you how to do this, find the dot product of two vectors. If I have the components of each vector, I don't need to use this. All I need to do is multiply each component by itself. And as you can see, 3 times 2 plus 4 times 5 is 26. But I can use this information to determine the angle in between, because since the angle in between can be found using this formula, if I already know that the dot product is 26 and I can figure out the magnitude of v and w, then in order to figure that out, I have the angle. Because I already know what the dot product is, I already know what the product of the two magnitudes are, and I can use inverse cosine to figure out the answer. What does the dot product mean? Basically, it's the measure of the alignment of the two vectors, or it's kind of like the measurement of the separation, or the measure of the rotation of the two angles of the vectors. Okay, couple things to note. Perfect alignment results in the largest possible value for u dot v. So perpendicular results is the dot product is equal to 0, because cosine of 90 degrees is 0. So if they're